So this is gonna be 1.6 limits involving infinity. Quite simple actually. So let's just get into it right away. And so I already have some stuff down. So what happens when the limit x approaches 0? And this is what a 1 over x squared graph looks like. I just know this, but you can kind of estimate this because as x approaches negative or positive infinity, then the output goes to 0. And same thing here. So it's kind of like dominance theory. You can assume that it goes to 0 here, and then it goes to infinity right there. So then the limit as x approaches 0 would simply just be 1 over the limit as x approaches 0. That looks a little strange. X of 0 of x squared, which is just infinity. Quite simple. So that's a limit involving infinity. This is another example here where the limit as x approaches a from, and this is a vertical asymptote here, and we labeled that as x equals a. So the limit as x approaches a from the left side will be infinity. So those are infinity graphs. So it's important to note, the limit as x approaches 0, well, the limit as x approaches a from the left side, right side, can either equal infinity or negative infinity. So let's go over one of the most important ones, or not necessarily important, but one that happens in real life, or not in real life, the one that you'll see often, and that is tan x. Sorry. And as everyone knows, if you took basic trigonometry, or geometry, or pre-calc, or algebra 2, it's sine x over cosine x. Guess what? Cosine x could equal 0. So there are vertical asymptotes. However, remember cosine x is periodic with a period of 2 pi. Or n 2 pi, I guess, for any matter. I mean, that's how you determine periodicity. So that means that every 2 pi cosine will be invalid. Let me think. No, it's actually every pi. So I guess we'll do n over pi over 2, which just crosses that out. So cosine x plus n pi should give us the periodicity of it. So this is what the sine graph looks like. And we'll do pi over 2 here and pi. So luckily, I know my trigonometric identities and trigonometric functions. And I know that, and we'll say this is 1 and negative 1. Actually, we don't even need to label this top part because it goes to infinity. And we'll say negative 1 here. So we know that cosine x is equal to 0 at integers of pi over 2 because that's when the adjacent side is equal to 0. So it looks something like this. Wait, cosine x. Wait, no, it looks something like, yes, like this. And it repeats like that. Wait, yes. Like, looks like something like this. And every time it reaches negative pi over 2, it goes to infinity. So the limit as x approaches, I guess it would be any integer of n pi over 2. So 2. Actually, no, that's not how it works. I'm thinking. Pi over 2 and 3 pi over 2. I guess periodicity would be 2n plus 1 pi over 2. They used I guess they use something from like the Clad's conjecture a little bit. Or I see that term in the Clad's conjecture. I guess it would be n pi over 2. No, that wouldn't work. I guess it would be pi over 2 plus n pi. Then cosine x will be, or tan x will go to infinity. But remember that it depends on the side. So as we see here, let's break this into left and right hand sided limits. So limit as x approaches pi over 2 from the left side appears to be infinity, and we'll say f of x, which is the same thing as tangent x here. But then the limit as x approaches pi over 2 from the right side appears to be approaching negative infinity. So this is an undefined limit, a DNE, as my teacher calls it. And yeah, that's an example where the left and right hand sided limits don't converge and go to infinity. Two different infinite values. And remember, infinity is not an actual thing. Infinity is a concept stating that something will get arbitrarily large. You can't actually have infinity. So that's where dominance theory arises. And infinity just means an arbitrarily large number. Let's go over another limit of infinity. But instead, we're not going to go over the limit as x approaches a finite value. Instead, now we're going to assume that a, in the limit notation, is going to be infinity. So what does that mean? Now let's take the graph x squared minus 1 over x squared plus 1. At x equals 0, it will be minus 1 plus 1. So I guess, and then we can use the dominance theory to assume that the end behavior asymptotes are going to be 1 respectively, because x squared and x squared will always be positive. So then if we have negative 1 and 1, the graph is going to look something like this. Like that. Yes, something like that. And guess what happens here, right? The limit as x approaches, and we'll say this function is f of x. X approaches infinity of f of x is what value? It will be 1. And the limit as x approaches negative infinity would be 1 as well. Note that for limits involving infinity, you don't need to know the left and right side. There's only one value you need to know, and that's as x gets arbitrarily large. And that's simply because we're not checking at one point necessarily. We're just checking an interval of values that are just getting increasingly large. And that technically includes the left and right side limit. It's a little bit difficult to explain, but that's the logic behind that. So yeah, horizontal asymptotes are the same thing as end behavior limits. So the limits as x approaches infinity of something, and the limit as x approaches infinity will always be the end behavior asymptote. So if the limit of x approaching infinity, sorry, I don't know what that is, of f of x is equal to 1, this is called the horizontal asymptote, meaning that the function will never actually touch 1. I mean, theoretically it could. So like, let me think of an example of what actually happens here. I'm thinking. Okay, I guess the best example would be 1 over x plus 1. So when x is equal to 0, I mean, I guess this would just be a translation to the left, so it would look like something like that. So, wait, can x reach 1 here? Yes. So x could hit 1 here. Yes, that's true. I'm trying to analyze this graph right here, so give me a second. X plus 1, yep. Seems right. But x could also be 1. Oh, yeah, x could be 1. Oh, sorry, because it would be 0 here. So x can't actually equal 0 here because this is a division quotient. Nothing divided by a number can give you a real number divided by anything cannot give you 0, but we can use limits, obviously. So, I mean, it's a little bit difficult to understand. I mean, not difficult, but an end behavior asymptote is the same thing as a horizontal asymptote, which is the same thing as x approaches infinity. What does the number reach? So we're going to go over and actually, we don't even need to know this one. We'll move on to the next one. I'm using my notes here, so I'm kind of trying to assume what we need and what we don't need. So let's go over the limit as x approaches infinity of 1 over x. Now, there's two ways you could solve this. First, you can go to your CAS calculator. That probably has a limit function, but of course, that's the cheating method. Instead, we can evaluate the limits, I guess using limit law, so I guess the division quotient here. So what is the limit as x approaches infinity of x? That means x is getting arbitrarily large, so it's the same thing as 1 divided by infinity, which is actually not a computable limit. And remember, infinity just represents an arbitrarily large number. So if it was like 99999, then it would be 0. Same thing to this other side. If x approaches negative infinity, that's become a very arbitrarily large negative number, and that will equal negative, or actually not even negative 0. I guess it's approaching 0, because at closer you get to, no matter how many numbers you get, it gets closer and closer to 0. Now we go over dominance theory. And I love this theory because my teacher was explaining it, and I never understood how the L'Hopital's rule was defined, but I guess you can kind of use it in this case. So we'll take 3x squared minus x minus 2, and then we'll do 5x squared plus 4x plus 1. And we'll say the limit as x approaches infinity because we need to. I mean, I guess it wouldn't really matter here if we use dominance theory because the x's are squared. But anyways, you can't do 3 times infinity squared divided by 5 infinity squared. What does that even give us? Like, how can you divide infinity and infinity? And, well, this is called an indeterminate form. And the two indeterminate forms that you'll deal with is 0 over 0 or infinity over infinity. And this is in the indeterminate form. Well, guess what? The rate of change here is what determines what actually happens. So 3x squared has an x squared term, and this has an x squared term. So that means this bottom one, that means these two terms are really the only ones deciding the trajectory of this thing. So like, let's plug in an arbitrarily large number. And we'll do 99999. And this top part, 99999 minus 2, guess what happens? Using some simple algebraic manipulation, we get 9998, 999999. This barely puts a dent in the thing. So instead, we can just ignore this entire term because these two ones are the only ones changing at a rapid rate. And these are the only ones that are basically determining the growth pattern of this. I mean, take these out and you'll get a linear function. And nobody wants a linear function here, and that will be such a small rate of change. But these ones are increasing very quickly, especially as x is approaching infinity. So we use dominance theory and say 3x squared divided by 5x squared is the only thing here. Use some algebraic manipulation to get 3 over 5. And the limit is 3 over 5. Because these are the only ones really deciding this. I mean, that literally changed like less than 1% of the entire thing. So, yeah, that's what we'll use there. So, I guess you can derive the L'Hopital's rule from that, which my idea was because we're only focusing on rates of change, then if you take the derivative, which is the instantaneous rate of change at any point, over and over, then you see which ones are changing at a rapid rate and which rates are changing and which ones actually matter. So that's kind of how I thought L'Hopital's rule was derived. It probably is, but I haven't looked into it, so. Okay, now we'll go over another one, and this is going to be with rationals. Not rationals, yes, rationals. Limit as x approaches infinity of square root x squared plus 1. Now, you can't use algebraic manipulation here. X squared plus 1 isn't easily factorable. I'm sure you can't actually factor it, matter of fact. Yes, I'm trying to think, but I don't think you can. Yeah, you can't. You can't split it into two even factors. But instead, we can rationalize the top and bottom. And to do so, we always do it by the conjugate. So it's going to be x squared minus 1. Wait. Oh, no. Oh, sorry. It was minus x. That was a little strange. So x squared plus 1 plus x, because you always multiply by the conjugate, which is just a plus b and the a minus b. If you guys know some basic algebraic manipulation, do some algebra here. X squared plus 1. Wait, I'm doing math. Oh no, those just cancel out. Wait. Yep, those just cancel out, giving us minus x squared. Over square root x squared plus 1 plus x. And this just becomes 1 over square root x squared plus 1 plus x. I guess you could apply dominance theory here. So we cross out the 1 because that doesn't even change the rate of change. So it becomes 1 over x plus x, which is 1 over 2x. And then you can plug in infinity, which will be 1 over 2 times infinity. And as everyone knows, as something is getting arbitrarily large on the denominator, it approaches 0. Let's do one more, and we're going to use the sine function here to prove that not every function has end behavior asymptotes. And those will typically deal with periodic functions because they just repeat infinitely. And we'll say f of x is equal to sine x. So what does a sine x graph look like? And I'm not going to draw it out. I'm not going to label it, but it looks like this. Notice how it's repeating over and over, and even at infinity, we can use some logic to deduce that, because since it's just multiples of 2 pi, it's just going to go like this over and over. There's nothing it's converging to, and that's why the limit of x as x approaches sine x does not exist, and you're going to have to use some logic to figure that out, but I'm not sure the way calculators do it. Now, we're going to do infinite limits of infinity. Just know that, and I'm going to try to simplify this so I don't have to write it out 4 times. So it's going to be limit as x approaches plus or minus infinity of a function can also be plus or minus infinity. It's basically what the theorem is stating. Let's do limit as x approaches infinity of x cubed, which is simply infinite cubed, which is infinity. Direct sub, or you can plug in an arbitrarily large number, and it'll keep getting bigger over and over again. Same thing as negative infinity, but this time, negative x, I guess you could just do negative infinity cubed, which is just equal to negative infinity cubed. So it will be negative infinitely large, so it would be limit as x approaches negative infinity of x cubed is equal to negative infinity. Yeah, I guess there's nothing really more we have to cover for that part. And wow, that's really it. Actually, I do want to go over something real quick, so I'll be right back. It's going to deal with precise definitions of limits. Oh, actually, it's right here. And we're going to have even further ones. Okay, here we go. So, This looks pretty good. Okay. So let f be a function defined on some open interval that contains the number a except possibly a. So again, same theorem. I guess a can be anywhere because it depends on where you evaluate the limit. Say right here. Oh, this is gonna be for definition 6, which is the limit as x approaches a finite value, going to infinity. Or negative infinity, plus or minus infinity. We know infinity here will be. That means a plus epsilon, or theta, I mean delta, a minus delta, and let's just say the graph looks something like this. Then there has to be, there has to be a line m where, x minus a has to be greater than 0, greater than epsilon, and then f of x has to be greater than m. Because, yeah, that's just what it is. So we'll do an example here. Actually, I'm not even going to do an example. I'm going to go through it, and then I'm going to explain how this actually works, because now I have a way better understanding of it, simply because I looked into all the intricacies of it. So then a limit at, so n behavior asymptotes, which we're dealing with here, of f of x is equal to L is the precise definition we're doing here. Let f of x be defined on some interval a to infinity. And it doesn't matter, we say a to infinity simply because we are using a not finite value. I mean, again, infinity is just an arbitrarily large number. Doesn't matter how large the number is, it just has to be bigger and bigger. So that means this is going to be L minus epsilon. This is going to be L right here. This is going to be epsilon, epsilon, L plus epsilon. And then we have this graph that's just going like this and that. Oh, we don't use A actually here, so let me erase these. Let me move this down. So n right here. So then the definition goes, and I'm gonna do it myself, so I'm not even gonna look at my paper. That if x is greater than a specific value n, and n will be positive here because we're approaching positive infinity, then f of x, I mean, I guess it would be then f of x has, oh wait, then f of x minus L has to be less than epsilon. And then we find the epsilon to n relation, and that's how we solve that one. Yep, logical here. And we'll do an example at the end, so don't worry. And then we'll do one more. And this will be a parabola because we're just gonna, and this one's gonna be infinity limits, and a limit of infinity at infinity. So if f of x equals infinity, this is quite easy. Then if this is a, then actually we'll just say m and n. They use m and n now for some reason. N x greater than n, then there has to be a value where or f of x is greater than m. Yes, that's all that means here. That's pretty self-explanatory there. And the last one, actually, I think there's two more. Wait, that is the last one. Okay, so let's go over some of these limits here. And first, let's go over the precise definition of a limit. So what is it trying to say? And I'm going to go over it one more time simply because it is very difficult to understand. So it is notoriously difficult to understand. So what we're going to do, I mean, even for college students, so we'll say 4x minus 12 is a function here. Actually, no, let's make it even better. I'm trying to think of something that will be easy. Let's just use an example here. Actually, I want to go over, okay, well, like 4x minus 5. That's what they used before. And it's not absolute value, so ignore this. 5 equals 7. So what does x minus a give you? Now the x minus a will always give you the distance that x is from 5. Because this is a difference, and then you absolute value the difference. So for example, if it's negative 5, and x is a positive number, then, wait, let me think. Wait, yes. Wait. Okay, so if it's from 5, then if it's 9, then it will give you a distance of 4. If it's 8, it will give you a distance of 3. If it's a negative number, then it'll exemplify the distance by adding the negative 3, which is just in. Anyways, this will give you the distance from A always. So A would be the limit point. So if it's like we're trying to find the limit right here, then this is A. And basically, we're seeing if we pick a point, then we're seeing how far that point is away. And that point will technically be delta here because we're denoting that as the distance that we're trying to measure. So for any distance from A, we can find an epsilon, or we can find a y value that corresponds to each of these distances away. It's basically what the proof is saying. So epsilon is greater than 0. So now the reason why we have to have it greater than 0 is because x can't actually be at A itself. That's not the definition of a limit. So that's why we need that there. It has to be less than epsilon, because if it's greater than epsilon, then it can go outside the range. I mean, these are the bounds that we need to define. Now 0 minus f of x minus 12, f of x minus, or L, f of x minus L, has to be greater than epsilon. So all that tells us is this function, so any input we put into this function here will always give us, or always has to be less than epsilon. And it doesn't have to be less than 0 here, because it could actually be at that point, which is quite logical. So what this does is for any value of x, it'll give us the distance from the limit. So that means regardless if we're all the way out here, it'll give us the distance from the limit right here. It will always give us the distance no matter how long or tall it is, right? So that should always work right there. And it has to be less than epsilon. So in other words, we're trying to get the outputs to match the input here. So to do so, and it's not x minus 5, it will be x minus 3 actually. And this should be 7, yes. Because that was not true. Then we have to find epsilon that matches delta. And simply put, we could just factor out a 4 here to get x minus 3 is greater than epsilon. So that means we just got the output and input relation. That means for whatever the output is, the input will always be 3 times smaller. Or however far the function is from the limit value, we just got that to see how far the input is from the input is from the limit A value. So simply put, all we did was get the output's limit. Wait, how do I say this? All we did was we got the distance from the output to the limit to the input to the limit inputs, and we simply related the two values. So that means that what the output value will always be 4 times greater than the input value, basically. Or the output value's distance from L, which is f of x minus L, will always be 4 times greater than x minus A. So that means that epsilon over 4, which will be the distance from the limit value, has to equal delta over 4. And the reason why we can't say that delta is epsilon over 3, for example, because if we say that x minus 3 is greater than epsilon over 3, that's not true, because if we solve this again, we'll get epsilon over 4. And if x minus 3 is less than a bigger epsilon value, then this can go outside the bounds, like probably right here, which will say epsilon over 3, which does not match the epsilon over 4 that we have. So that is the logic here. We'll do a proof here, and I'm going to use my... Whoa, I don't know what just happened. Oh, I kind of like that, actually. I kind of like that. Okay, so so let's say 2. Let's say 4 is equal to 16. Then we'll do the proof here for one of the values. So remember that the proof here is that if x is greater than n, then f of x has to be greater than m. Yes, and it's not absolute value, so you don't have to worry about that. So x minus 4 is greater. The absolute value is what what throws people off sometimes. So I don't have to put absolute value because x is already defined as greater than 4, because it's... Wait, no. No, you would still need the absolute value. Sorry. Oh, wait, we're not doing limits at infinity. Sorry. It's incorrect. If the limit as x approaches infinity of infinity. That's what it was. Sorry, that threw me off. So then we have to find an n value, and we have to... And we can use any point on the graph because the graph appears to be homogeneous. So n and m. This is quite simple. I mean, I can use simple logic. M will always be squared of n. So that means that if m is denoted as epsilon, then n has to be square root epsilon because the input is square root this, which is just x. So that's simple logic there. I can use simple logic, but instead I'm not going to here. So then we're just going to use the logic here. That x minus n. And we can denote n as any number, I guess. And we'll do 4. Or actually, let's just use symbols. So x has to be greater than n, and then x squared has to be greater than m. Just square root it. So that means that means x squared will always, x in x squared will always be greater than square root m. And since this has to be greater than an arbitrary n value, we have to say it has to be greater than square root m. Because if we say that it's any smaller, then there can be an interval in which that x is greater than n, but small, or greater than, let's just say like m 1/3, or m to the power of 1/3. That m is greater than this value, and that doesn't work. Because if we denote x as anything else, anything small, we can use a smaller n here, but we cannot use a greater n here. Because if we use a greater n, then what happens is, let me think. Yeah, we can't use a greater n, but we can use a smaller n. Wait, can we use a smaller n? Sorry, this is like killing my brain right now. Okay. So, I mean, I guess I could just do the math. So if it's 4... No, I guess no, you have to just substitute it in because you have to keep the relationship. So that's 1.6. Hope that wasn't too long, so that's understanding.